Welcome to the Cool Coolers project. Food production takes up 1/3 of the world's energy requirements. The resources that go towards growing our food are truly staggering. Until recently in our history, almost the whole of society was devoted to food production. So, for something as energy expensive, labor intensive, and central to our lives as food, why do we waste so much of it? In today's modern world, we often lose track of what's in our own fridge, and this leads to waste on a colossal scale. The right foods are essential for a healthy lifestyle, and yet we often struggle to keep on top of our own inventory, leading to many wasted moments wandering to the fridge for a fruitless look inside. Enter the Cool Coolers.
The purpose of the hardware is to take photos of what's in your fridge. To do this, we need to have a camera in there. The average person has a lot of stuff in their fridge and we only have one camera. So we started looking at different designs for moving the camera around, taking inspiration from 3D printers, CNCs and camera rigs. We got the electronics out and started to mock up some systems, some more sophisticated than others. We ran into some issues, but eventually we got a nice dual motor set up for moving the camera around. We started to work with the ESPi, initializing the camera to capture a suite of 3 photos when prompted by the motor controller. When we were happy with the idea, we started to design and print parts, again of varying sophistication, before arriving at a good design for a spooling coil to move the ESPi along parallel rods. And so the printing began, and thus began the cycle of designing, prototyping, and breaking components. Iterating this produced some really nice products that were completely fit for purpose. And when we had the final design finally printed, we were ready for a systems test. And it worked! Look at it go, it's brilliant. So I've skipped over most of the programming as the GitHubs are linked and they have an explanation of the program's purpose and functionality if you care about that.
Our cloud deployment was built in Amazon Web Services to enable communication between the ESP, cloud storage, and the user application. We built an API gateway to trigger a Lambda function, which returns a signed URL, which is used to upload images from the ESP to S3, our file storage. The images are stored in a folder unique to the registered device, and a reference to the image is stored in DynamoDB. Docker containers are deployed to carry out image recognition through another API. This will be talked about in the next section. The results of the image analysis are retrieved by the user application upon sign-in through another API and are viewable in the app. HTTPS protocol was used in this project. A stretch goal was to implement two-way communication between cloud and ESP, but this was not achievable in the time constraints. This would be the next step in the project and would involve using MQTT over HTTPS. Now allow me to give you a brief overview of our cloud solution. We have 3 Lambda functions in AWS: capture fridge image, get item list, and return signed URL. These should all be self-explanatory now that you know the flow of our cloud solution. Next we have our S3 bucket, which is our file storage, within which we have a folder with a unique name for each device that is registered. Within this folder is a list of all of the images that have been uploaded from the ESP to the bucket. And this is where the magic happens, our DynamoDB, which is linked through an API. So we also have all of the images linked to the S3 bucket, as well as the results of the object detection and inference. So for each image, we have a list of all of the items detected in the fridge. So we can see that at some point Senan had a bottle, at another point he had a banana and 6 apples. This is the joy that we can bring.
Now, the machine learning aspects of this project. Here is the plan. We call it the FIDA. First, for this project, it's necessary to train the models using the custom dataset to detect the various kinds of food that we might keep in our fridge. But we could not achieve this goal as it's impossible to collect the data and label them in a very short period of time that we had. But that didn't stop us from going further. We used pre-trained models from Facebook's Detectron 2 framework to detect the limited amount of fruits and vegetables for now. Using the Detectron, we built a Flask application which serves as an endpoint for object detection as a service, and we deployed it in the AWS cloud as a Docker image. We have used GitHub Actions to automate the build and deployment flow. On updating the repository, a Docker image is built and it will be pushed to Amazon ECR, the container registry in AWS, like this. And we have configured the image to be started as a Elastic Container Service to serve as an endpoint, which can then be used by a Lambda function that is triggered on uploading the image to our S3 bucket.
Now we will look at our Android app, which is the Cool Coolers app. Once we click on this icon, we will see the register page. So here we could register a user. We already have registered users, so we won't do that now. Now we will click on the already have an account button to go on to the login page. Here we can enter the email and password to login. I will just enter the password quickly. Once we log in, we can see the contents of the fridge. This is the first deck of the fridge. It shows 1 banana, 1 apple, and 4 bottles. If we click on the next, we can see the medium layer of the fridge. It has 1 banana and 3 apples. If we click on the next, we will be able to see the last deck of the fridge. It has 2 apples. If we go on previous, we can see the previous items. If we go on previous, we can see the first layer. Thank you.
So in summary, this is us. Your 4 fine fridge folk. Barath, Adam, Senan and Karen. We're making a fridge smarter than you've ever seen. We started this project with a dream and several ESP32s. From there we mocked up electronics to take photos, move motors and communicate over Bluetooth and Wi-Fi. Next we began mocking up systems to navigate the fridge space, altering the position of the ESPI in order to take photos of the interior from different perspectives, increase the robustness of our food item detection and recognition system, used to detect and spatially position food items and then to recognize it. This food item data can be tracked and used in many ways, which brings us to our customer. It's you. When you put us in your fridge, you'll be amazed with how smart we are. What we'll be doing there is keeping track of your household eating habits, creating shopping lists of what you've used, logging your favourite food based on how long it remains in your fridge, and creating recipes based on what's in your current fridge. But there's a little bit more. The end goal of our system is an open source, maker-friendly, smart fridge development platform that's cheap enough that us poor students will be able to afford it, and effective enough that you'll never want a dumb fridge again. And from all of us at the Cool Coolers, we just want to say thank you for bringing us together, entertaining us, and making this all possible.